curl. The curl in magnetostatics can be written in J is equal to del cross H. The current density is equal to the curl of the magnetic field intensity. That is, the current density is equal to the curl of the magnetic field intensity. J is equal to del cross H. So that J is equal to Jx Ax plus Jy Ay plus Jz Az. That is, J is equal to Ax Ay Az. That is cross product dou by dou x, dou by dou y, dou by dou z, hx, hy, hz in Cartesian systems. That is in the coordinate values x, y, z. In cylindrical coordinate system r, pi, z. That is, J is equal to 1 upon r, ar, r, a pi, az, dou by dou r, dou by dou pi, dou by dou z, hr, r, h pi, hz. That is, in cylindrical coordinate system, the curl can be written. In spherical coordinate system, r, theta, pi, J is equal to 1 upon r square sin theta. That is the cross product. That is curl. How it can be written in the spherical coordinate system? ar, r, a theta, r sin theta, a pi, dou by dou r, dou by dou theta, dou by dou pi, hr, r, h theta, r sin theta, h pi. Stokes theorem. The surface S is divided into a small incremental surfaces of area delta S. Here, this one, it is a surface. This surface, it is divided into small incremental surfaces of area, that is delta S. That is, here this is a total surface S, and here these are the incremental surfaces within that total surface. Now, del cross H is equal to closed integral H dot dl delta S upon delta S. Normal to the incremental surface area delta S is En. Normal to the incremental surface area delta S is En. That the del cross H is equal to del cross H dot En. Del cross H dot delta S is equal to del cross H dot En delta S, because this normal to the incremental surface area is En. That is, here it is a incremental surface area, normal to that it is En. So that this the del cross H is equal to del cross H dot En. Now, del cross H dot delta S is equal to del cross H dot En delta S. En is a unit vector normal to that the incremental surface. Here, this one, it is the incremental surface, and En, it is a normal to that incremental surface. Closed integral H dot dl delta S is equal to del cross H dot delta S. Del cross H dot delta S, because dl is a perimeter of the incremental surface, delta S area of that incremental surface. So that here the total curl due to the entire surface, it is closed integral H dot dl delta S is equal to del cross H dot delta S, because this is only due to one incremental surface. This surface, it is divided into small incremental surfaces, and whatever that the closed integral H dot dl delta S is equal to delta del cross H dot delta S. dl is a perimeter of incremental surface, area delta S area of incremental surface. So that the total curl due to entire surface is equal to the sum of the line integral of each incremental surface. The total curl due to entire incremental surface, the total curl due to entire surface is equal to the total curl due to the entire surface is equal to the sum of the line integral of each incremental surface. The total curl due to entire surface is equal to the sum of the line integrals of each incremental surface. The line integral of incremental surfaces cancel. The line integrals of incremental surfaces cancel because the line integral is traced in the opposite directions. The total curl is reduced to a single line integral obtained at the boundary of the surface, because here the line integrals of the adjacent incremental surface areas cancel each other because these are traced in the opposite directions, so that the total curl is reduced to a single line integral obtained at the boundary of the surface. So that closed integral h dot dl is equal to integral s del cross h dot ds. So that the statement, the line integral of magnetic field intensity, H, the line integral of magnetic field intensity H around a closed path is equal to the integral of curl of magnetic field intensity is equal to the integral of curl of magnetic field intensity within the surface. Integral of curl of magnetic field intensity within the surface enclosed by the closed path. That is equal to h around a closed path. The line integral of magnetic field intensity h around a closed path is equal to the integral of curl of magnetic field intensity within the surface enclosed by that closed path. That is the statement of the Stokes theorem. Stokes theorem is used to convert line integral to the surface integrals. In magnetostatics, as divergence theorem is used to convert surface integrals, as a divergence theorem is used to convert surface integral to volume integral in electrostatics. Stokes theorem is used to convert line integral to the surface integral in magnetostatics, as the divergence theorem is used to convert surface integral to the volume integral in electrostatics. Evaluate both the sides of the Stokes theorem for the field H is equal to 6xy ax minus 3y square ay ampere per meter and the rectangular path around the region 2 less than or equal to x less than or equal to 5, minus 1 less than or equal to y less than or equal to 1, z is equal to 0. Let the positive direction of ds be a z directions, so that the closed integral h dot dl is equal to integral a to b h dot dl plus b to c h dot dl and c to d h dot dl. Here a closed surface, it is of these forms, that is the as in the problem itself it is shown that the it is of this value h is equal to 6x and a rectangular path around the region x less minus 1 less than z is equal to, let the possible direction of ds be z directions. Here to determine that closed line integrals, for that one the integral a to b h dot dl is equal to a to b h dot dl is equal to 2 to 5. A to b is 2 to 5, 6xy x dot dx az, because here it is along the x directions. This rectangular path, one of the side of that rectangular path, it is along the x directions. That's why while taking the divergence only x component is considered. So that 6 into bracket of x square by 2 into the 5 to 2, that is the here it is the integrals from 2 to 5. Now the 6 into bracket of x square by 2, 2 to 5, 6 by 2 25, it is 25 minus 4, it is equal to 321, 3 into bracket of 21 into bracket of y, that is the equations will be y is equal to minus 1 along the path AB. So that here the at this point y is equal to minus 1, so that 63 into minus 1 is equal to minus 63. Now the integral b to c, here integral b to c h dot dl, it is equal to, here the it is for along this path, along the one of the side of the rectangular path ABCD, it is path the BC, it is varies only along the y directions. So that b to c h dot dl is equal to minus 1 to plus 1 minus 3y square ay dot dy ay minus 3 into bracket of y cube upon 3 minus 1 to plus 1 minus 3 by 3 into bracket of 1 minus into bracket of minus 1, it is equal to minus 1 into bracket of 2, it is equal to minus 2. Now integral c to d, integral c to d h dot dl is equal to, here at a point since it is placed along the x directions, the integrals 5 to 2 6xy ax dot dx ax, 6 into bracket of x square by 2, 5 to 2 into bracket of y, 6 by 2, 4 minus 25 into y, 3 into bracket of minus 21 into y, it is equal to minus 63. Here c to d it is equal to minus 63. The c to d h dot dl. Now d to a, integral d to a h dot dl is equal to integral plus 1 to minus 1 minus 3y square dy is equal to minus 3 into bracket of y cube upon 3 minus 3, because here d to a it is varies only along the y directions, it is varies only along the y directions, as it is given 6xy minus ax minus 3y square ay, so that due to which the minus 3y square dy it is equal to minus 3 into bracket of y cube by 3 is equal to plus 2. So that here close total, that is the line into magnetic field intensity due to the entire rectangular path, it is equal to minus 63 minus 2 minus 63 plus 2 is equal to minus 126. Here that is the closed integral h dot dl is equal to minus 126. That is the equation for the that is the equation for the closed integral h dot dl, value of h dot dl. Now this is the one of the left hand side of that the Stokes theorem. Now according to that Stokes theorem, the closed integral h dot dl is equal to del cross h dot ds. The both the sides must be same, so that del cross h is equal to ax ay az dou by dou x dou by dou y dou by dou z is 6xy minus 3y square 0 dou by dou x dou by dou y dou by dou z 6xy minus 3y square, and here this one it is 0 plus 0 ax here 0 minus 0, here this one it is 0, and here the dou by dou z of 6xy it is 0, and here dou by dou x of 0 it is 0, say y, and here for this one it is the dou by dou x of minus 3y square it is 0, dou by dou y of here it is minus 6x az, del cross h is minus 6x az. In Cartesian system, the differential surface area along az direction is ds is equal to dx dy az. Del cross h dot ds is equal to integral y is equal to minus 1 to plus 1, and x is equal to 2 to 5, and x is equal to 2 to 5, so that minus 6x az dot dx dy az, and minus 6x into bracket of minus 6 into bracket of x square by 2 to 5 by minus 1 to plus 1, minus 6 by 2 into bracket 25 minus 4 is equal to 1 plus 1, 3 into 21 into minus 3 into 21 into 2 minus 126, so that the left hand side is equal to right hand side. Hence with sides of Stokes theorem, both the sides of Stokes theorem is verified. Magnetic flux and flux density. The magnetic flux density is related to the magnetic field intensity through the permeability of the mediums, that is B is equal to mu h. Magnetic flux and flux density. Magnetic flux density is related to the magnetic field intensity through the permeability of the mediums. B is equal to mu h. Magnetic flux density in Weber per meter square is equal to the magnetic flux in Webers passing through a per unit area of a plane, placed at right angles to the direction of the flux. The magnetic field intensity through the permeability of the medium. Magnetic flux density in Weber per meter square is equal to the magnetic flux in Webers passing through per unit area of a plane placed at right angles to the direction of the flux. If flux lines are not perpendicular to the plane, then equation for the magnetic flux can be written as pi is equal to integral s b dot ds. A single isolated magnetic pole can't exist. The flux within the closed surface is equal to 0. That is, pi is equal to closed integral b dot ds, it is equal to 0. According to divergence theorem, surface integrals can be converted into volume integrals, so that integral b dot ds is equal to integral v del dot b dv, it is equal to 0. So that the volume can't be equal to 0, that the del dot b is equal to del dot b, it is equal to volume can't be equal to 0, so that the del dot b it is equal to 0, so that the Gauss law in point form in magnetostatics. In cylindrical coordinates b is equal to 2 by r a pi, determine the magnetic flux pi crossing the plane surface defined by 0.5 less than or equal to r less than or equal to in cylindrical coordinates b is equal to 2 upon r a pi, determine the magnetic flux pi passing through the plane surface defined by 2.5 less than or equal to r less than or equal to 2.25 and z less than or equal to and r less than or equal to 0 less than or equal to z less than or equal to 2 meters. Now the magnetic flux it can be determined by closed integral b dot ds d b is equal to 2.0 upon r into a pi dot d pi. 2.0 upon r a pi dot ds, so that the flux density it is in pi directions, ds it is also in pi direction of cylindrical coordinate systems. Coordinate system ds is equal to ar dz d pi a pi, so that pi is equal to integral here pi is equal to integral r is equal to 0.5 to 2.5, z is equal to 0 to 2.0 upon r a pi dot dr d pi a pi. Pi is equal to 2.0 integral r is equal to 0.5 to 2.0 upon the r dr dz, so that here r is equal to 0.5 to 5, 0 to 2, so that 1 upon r dr dz 20 log of r here the pi r z 0 to 2 1 by r dr dz. Pi is equal to 2.0 into bracket of log of r integral 0.5 to 2.5 bracket of z 0 to 2. Pi is equal to 2.0 log of the 2 plus 5 minus log of x. Pi is equal to 22 log of 2.5 upon 0.5 into 2 is equal to 6.43 Webers. Find the flux passing through the portion of the plane pi is equal to pi by 4 defined by 0.001 less than r less than 0.05 meters and 0 less than 2 less than 2 meters. A current filament of 2.5 ampere is along the z axis in the az direction. A current filament of 2.5 ampere is along the z-axis in the az direction in the free space. Here h is equal to I upon 2 pi r a pi, h is equal to 2.5 upon 2 pi r a pi, b is equal to mu naught h, b is equal to 4.10 raised to minus 7 into 2.5 upon 2 pi r, b is equal to 5 into 10 raised to minus 7 r a pi. Is equal to closed integral v dot ds flux density. Magnetic flux density in a pi direction is magnetic pi is equal to close b dot ds. Magnetic flux in pi directions is equal ds is equal to dr dz a pi in cylindrical coordinate systems. Z is equal to 0 to 2, r is equal to 0.01 to 0.5. A is equal to 5 into 10 raised to minus 7 log of r. Five into 10 raised to minus 7 log of r, and 5 into 10 raised to minus 7 log of 0.05 by 0.01 to 0.09 into 10 raised to minus 2, 1.609 microweavers. That is the how we shall determine the flux passing through a plane placed at a right angles to the direction of the magnetic field. Scalar and vector magnetic potentials. Del cross del Vm it is equal to 0, del dot del cross A it is equal to 0. The curl of the gradient of a scalar is equal to 0. The divergence of the curl of a vector is equal to vector quantity. First one, the del cross del, the curl of the gradient of a scalar is equal to 0. Divergence of the curl of a vector is equal to 0. Divergence of the curl of a vector, the curl of the gradient of a scalar it is equal to 0. Del cross del Vm is equal to 0, scalar magnetic potential. Vm is scalar magnetic potential, H is equal to minus del Vm. Magnetic field intensity is equal to the negative gradient of potential. So that H is del cross minus H is equal to 0, del cross H is equal to 0, but del cross H is equal to J. So J is equal to 0. Scalar magnetic potential can be defined for source free region, that is H is equal to minus del Vm only for J is equal to 0. Poisson's equation for scalar magnetic potential. Closed integral as B dot ds it is equal to 0. According to divergence theorem, the closed integral B dot ds it is equal to integral V del dot B into bracket of dV it is equal to 0. Divergence theorem. So the del dot B it is equal to 0. So del dot mu naught H it is equal to 0. Del dot H is equal to 0 because mu naught not equal to 0. Here the B is equal to mu naught H. Here from the del dot H is equal to 0. H is equal to minus del Vm. Del dot del Vm it is equal to 0. Del dot del equal del square Vm is equal to 0. That is the Poisson's equation for scalar magnetic potential. Here the vector magnetic potential A, you know that the divergence of the curl of a vector it is equal to 0. Del dot del cross A it is equal to 0. Magnetic flux density is equal to curl of the vector magnetic potential. Del dot B it is equal to 0. B is equal to del cross A. That is the magnetic flux density is equal to the curl of the magnetic vector, curl of vector magnetic potential, the del cross A. A is vector magnetic potential. Here you know that del cross H is equal to J, del cross B by mu naught is equal to J, and the del cross B is equal to mu naught J. B is equal to del cross B it is equal to mu naught J. B is equal to del cross A. Del cross A is equal to mu naught J. Del cross A is equal to del dot A minus del square. Del dot A minus del square A is equal to mu naught J, but del dot A it is equal to 0 From that one, del square A it is equal to minus mu naught J, because this one it is Poisson's equation for the vector magnetic potential. Del square A is equal to minus mu naught J is equal to Poisson's equation for the vector magnetic potential. A flat perfectly conducting surface in xy plane is situated in a magnetic field H is equal to 3 cos x ax plus z cos x ay ampere per meter for x greater than or equal to 0. Find the current density on the conductor surface. So that here J is equal to del cross H ax ay az and dou by dou x dou by dou y dou by dou z. 3 cos x z cos x 0, dou by dou y 0, dou by dou z cos x, so that dou by dou z and dou by dou x z cos x it is equal to, because dou by dou y, and here for ay it is dou by dou z dou x, so that for the dou by dou x z cos x minus dou, so that minus cos x ax minus cos x ax minus z sin x minus z sin x az for z greater than or equal to 0 minus cos x az minus cos x az ampere per meter square. Evaluate both the sides of Stokes theorem for the field H is equal to tan sin theta a pi and the surface r is equal to 3, 0 less than or equal to theta less than 0 less than pi less than. Let the surface have the AR directions. According to the Stokes theorem, closed integral h dot dl is equal to closed integral del cross h dot ds. So that in spherical coordinate system, dl is equal to dr ar plus r d theta a pi plus r sin theta d pi a pi. H varies in the pi direction only, so that closed integral h dot dl is equal to closed integral tan sin theta a pi tan sin theta a pi dot r sin theta d pi a pi. Here tan sin theta a pi dot r sin theta d pi a pi, because here it is in the r direction, and the differential surface area it is in the r directions, and the magnetic field intensity it is also in the radial directions. So that closed integral tan r into sin square theta d pi a pi dot a pi tan r sin square theta into bracket of d pi tan r sin square theta d pi is equal to 10 into here it is the 3 into sin square 90 degree pi 0 to 90 degree 47.12, that is left hand side. R is equal to 3, 0 less than or theta less than or 90 degree, 0 less than or equal to pi less than or equal to 90 degree, that is the closed integral h dot dl. Now closed into del cross h dot ds is, that is the right hand side, del cross h is equal to 1 upon r square sin theta ar r a theta r sin theta a pi dou by dou r dou by dou theta dou by dou pi 0 0 r sin theta upon tan sin theta r sin theta into bracket of tan sin theta in spherical coordinate systems. Del cross h is 1 upon r square sin theta dou by dou theta r sin theta tan sin theta minus pi, because dou by dou theta of r sin theta tan sin theta minus here, and anyway that is dou by dou theta it is equal to 0. Now plus 1 by r square sin theta dou by dou r sin theta into tan sin theta plus dou by dou r plus 1 by r sin theta dou by dou r r sin theta tan sin theta into r a theta is equal to 1 upon r square sin theta dou by dou theta tan r sin square theta ar and r upon r square sin theta dou by dou r sin square theta a theta. Here 1 upon r sin theta dou by dou theta tan sin square theta ar plus 1 upon sin theta into tan sin square theta a. 10 upon r sin theta 2 sin theta cos theta ar plus 10 sin theta ap 20 by r cos theta ar plus 10 by r sin theta a theta. In a spherical coordinate system, the differential surface area along the radial direction is ds r square sin theta d theta d pi ar, so that integral s del cross h dot ds integral theta is equal to 0 to pi by 2 pi is equal to 0 to pi by 2 20 by r cos theta ar dot here r square sin theta d theta d pi ar. Integral theta is 0 to pi by 2 pi is equal to 0 to pi by 2 20 r cos theta sin theta d theta d pi. Integral theta is equal to 0 to pi by 2 pi is equal to 0 to pi by 2 10 into bracket of r 2 sin theta cos theta d pi 10 into bracket of r integral theta is equal to 0 to pi by 2 pi is equal to 0 to pi by 2 sin 2 theta d pi, because here the 2 sin theta cos theta, so that cos sin 2 theta d pi cos into bracket of minus cos 2 pi by is equal to 10 into bracket of r theta 0 to pi by 2 pi is equal to 0 to pi by 2 sin 2 theta d pi bracket of r minus cos 2 theta by 2 integral pi 0 to pi by 2, because sin 2 theta is cos 2 theta upon 2 10 r upon 2 minus into bracket of cos pi minus cos 0 pi by 2 minus 0 into 3 upon 2 it is equal to minus into bracket of the minus 1 pi by 2 minus 0 15 into 2 pi by 2 47.12. So that left hand side it is equal to right hand side, so that both the sides of the Stokes theorem are verified. Closed integral h dot dl is equal to integral s del cross h dot ds, that is both the sides are verified. The magnetic forces. The force exerted on a static electric charge placed in an electric field is given by is equal to QE, so that the force exerted on a moving point charge in a magnetic field is given by Fm is equal to Q into bracket of V cross B. Here this is F is equal to, in electrostatics it is QE, in magnetostatics it is Q into E cross B. The charge Q is moving with a velocity V in a magnetic field B. The direction of force is perpendicular to the plane containing channels V and B. Moving with a velocity v in a magnetic field V, the direction of the force is perpendicular to the plane containing V and V, then Fm is equal to Q. The theta is the angle between the magnetic field and the velocity with which the charge Q is moving in a magnetic field. So that this theta, it is the angle between these two. The total field strength, that is the total force exerted on a charge Q in a electric field and magnetic field. The field is given by f of t is equal to Fe plus Fm is equal to f of t is equal to Qe plus Qe. F of t is equal to Qe plus Q into E cross B is equal to F total force, it is equal to Ft into bracket of. That is the here total force F of t is equal to Q into bracket of E plus V cross B it is Newton. This equation is known as Lorentz force equation. A point charge of q is equal to minus 1.2 coulomb has a velocity v is equal to 5x plus 2ay minus 3az meter per second. Find the magnitude of the force exerted on the charge if e is equal to minus 18x plus 5ay minus 10az. B is equal to minus 4x plus 4ay plus 3az. Both are present simultaneously. Here f of e, that is the force exerted on the charge q in a magnetic field E, is given by f of e is equal to minus 1.2 into bracket of minus 18x plus 5ay plus 10az is equal to f is 25.42 is q into bracket of v cross b minus 1.2 into bracket of x plus 2 minus 3az. So that the force in magnetic field is v cross b, it is equal to ax ay 5 2 3 minus 4 4 3. So that the force exerted in the magnetic field on a charge moving with a velocity is minus 1.2 into bracket of 6 plus 12x 12 minus 15ay 20 plus 6az 1.2 into bracket of 18x plus minus 30y plus 28az minus the magnetic field magnitude of the magnetic force is square root of is equal to magnitude of the force exerted in the magnetic field it is equal to 40.10. F of t, that is total force due to combination of the electric and magnetic fields, it is equal to E1 plus the F1 plus Fm. F t is equal to minus 21 plus 21 minus 6ay plus 12az. So that F of t is equal to 0 minus 2.4ay minus 21.60az. Modulus of F1 is equal to square root of 5.76 plus 46.566. Flux of Et, it is equal to 21.73 newtons meters. Force between two differential current elements. Current flowing through two conductors placed separated by a small distance is in the same direction. Then the two conductors experience a force of attraction. If the current is flowing through the conductors in the same directions, the current flowing through the conductors, it is in the same direction. Experience a force of attraction. If the currents flowing through the two conductors are in opposite direction, then there is a force of repulsion between the two conductors. The differential current of conductor 1 is I1 dl1. The differential current element of conductor 2 is the distance between the two conductors in R. The distance between the two conductors in R. The force on conductor 1 due to the field produced by a conductor 2. D of df1 is equal to I1 dl1 cross dv2. dv2 is equal to mu naught dh2. According to the Boyd-Savart's law, the magnetic field intensity is dh2 is equal to I2 dl2 cross 4 2 upon 4 pi r2 square. R21 AR21. Now dv2 is equal to that is according to the Boyd-Savart's law, the magnetic field intensity dh2 is equal to I1 dl2 cross AR21 4 pi r21 square. dv2 is equal to mu naught into bracket of I2 dl2 cross AR21 upon 4 pi r21 square. D of df1 is equal to I1 dl1 cross mu naught into bracket of the I2 dl2 cross AR21 upon 4 pi r21 square. D of df1 is equal to I1 I2 mu naught upon 4 pi r21 square into closed integral L1 closed integral L2 dl1 cross dl2 cross that is AR21. Now D of df2, that is force exerted on conductor 2 due to the field produced by conductor 1 is df2 is I2 dl2 cross dv1. dv1 is equal to mu naught dh1. According to Bird's law, the magnetic field intensity dh1 is equal to I1 dl1 cross r12 upon 4 pi r12 square. So that dv2 it is equal to mu naught dh2. dv2 is equal to mu naught dh2. So that here this is the magnetic field produced flux density due to the second conductors, due to magnetic flux density due to a conductor of the magnetic flux density of the conductor 2. df2 is equal to I2 I1 mu naught upon 4 pi r12 square closed integral L1 closed integral L2 dl2 cross dl1 cross ar12 upon ar12. So that from equations 1 and 2, the force between the two conductors carrying currents I1 and I2, if the length of the conductors is L and separated by a distance d, is F is equal to mu naught I1 I2 L upon 2 pi d. That is the force between the two conductors carrying current I1 and I2 separated by distance d and having length, it is equal to L. Now magnetic circuits. Magnetomotive force mmf is measured in terms of Ampere's law. Magnetomotive force mmf is measured in ampere terms. mmf is current passing through the conductors, so that mmf is equal to the conductor. It is mmf is equal to Ni. The reluctance is